Everyone, and welcome to this series of PEO exam questions. And this is for electrical B7 power systems engineering. And this question is about transformer. If you recall, for electrical A6, there are some other transformers question as well, but there the questions are basically for the open and the short circuit test. Here is the questions and this is one example of them. This is the exam of May 2019, is basically about analyzing the transformer circuit. So you know the model and you are analyzing it. So let's see this question. Here it says this is a 50 kVA. So this is the rated S value of the transformer, 2400 by 240. So this is a step down transformer. This is the high voltage side and this is the low voltage side. 60 hertz single phase has the following values. So we know the R equivalent, X equivalent, XM and RC, and use the equivalent cantilever model, which is this one. We call it sometimes the approximate model, assuming the load on the secondary side is this lagging and the receiving end voltage maintained at 240 volt. Okay, now these values are referred to the high voltage side. This is very, very important. So this model is taking at the high voltage side, which is the primary side. Now, when we take the model referred to the primary side or the high voltage side, V1 and I2 stay as they are, but here the current will be, when we refer it to the high voltage side, will be I2 over A, and this will be AV2. Okay, and A is the ratio. A is basically is equal to 10. So for this, your model will be as such. This is the model that we will be used in this question. Let me have the value. R equivalent is 0.5, and this is J3, and XM is J4.5 kilo ohms, and this is R is 30 kilo ohm. Now this is your AV2. Now it says here, assume that the receiving end maintain at 240, but because this is the model referred to the high voltage side, it will be A times V2, which is 2400 volt, and here is your I2 over A. Then the question says here, the first one, find the voltage at the primary side. So we want to find V1, this voltage. Now to find this voltage, we need to apply KVL. Now we know everything except I2 over A. Now here, this is the first part. Your I2 over A is equal to your rated value or the S, which is here, given to you at 40 kVA, which is less than the rated value. Sometimes they will tell you, assume the load is the rated load, which will be 50 kVA. This time is less. So this is equal to 40 times 10 to power 3 divided by the voltage, which is 2400. And the angle will be, it's a 0.8 lagging minus cosine inverse of 0.8. Now this voltage will have an angle of 0. This will be our reference. So the current will be 16.67, angle of minus 36.9. Now what will be your V1? KVL, your V1 will be equal to the 2400 angle of 0, which is this voltage, plus the voltage drop, which is 16.67 minus 36.9 times the impedance of the winding, which is the 0.5 plus J3, and this will give me a voltage equal to 2436.9 and an angle of 0.82. Number 2, find the current in the primary. Now the current in the primary, which is I1 is equal to, of course, I2 over A plus the current that goes in the RC, which is, I will call it IC, plus the current that goes through IM, or the inductive part of the core, which is IM. Now we need to find IC and we need to find IM because we already know I2 over A. So your IC, Ohm's law, is equal to the voltage V1 across it divided by the 30K. So IC is nothing but 2436.9 angle of 0.82, which is this voltage, divided by the 30K, or 30 times 10 to the power 3. And this will give me a current 0.0812 angle of 0.82 amps. On the other hand, your IM is equal to 2436.9 angle of 0.82 divided by 4.5 times 10 to the power 3, because this is J, this becomes plus 90. And this give me a current 0.94 angle of minus 89.18 amps. So now we know all the three currents. So from this, your I1 will be the summation of these three currents. And this will give me 17.06 angle of minus 38.15 amps. So this is your primary current I1. Then let's move on here. Find the active power input. So we need to find the active power input. Your P input equal to the voltage V1 times I1 cosine of theta V1 minus theta of I1. We have all the information. So your V1 is 2436.9 times I1, which is 17.06, cosine theta V1 is 0.82 minus 38.15, which is the angle of the current. So when you do this, you will find this is equal to 32.32 kilowatt. So we're done with this. Number 4, find the reactive power, the input, again, the reactive power input. So the Qn is equal to the same formula, but instead of cosine, we'll have it as a sine. So it's V1, I1 sine of theta V1 minus theta I1, which is equal to 2436.9. This is times 17.06 sine of 0.82 minus 38.15. And this will give me 26.15 kVAR. So we found the active and the reactive power. Number 5, it says find the power factor at the primary side. As we know, the power factor is equal to cosine theta V1 minus theta I1, because this is at the primary side. These are the voltages and the currents and the primary side. So this is equal to cosine of 0.82 minus 38.15, and this will give me 0.78 lagging. You have to remember that. You have to write the value and you have to specify if it is leading or lagging. And why it is lagging? Because the current lags the voltage. The current angle is negative 38.15. The angle of the voltage is 0.82. If I want to draw a phasor diagram for this, this will be the voltage. This is your V1, and this will be your I1. So the current here is basically lagging the voltage. This is why we call it a lagging power factor. Finally, we want to find the efficiency at this loading, which is the 40 kVA. The efficiency is nothing but P out over Pn. P out, we have it. It's the 40 kVA times the power factor, the 0.8. just to remind you, comes from the power triangle. This is your S, this is your P, this is your Q, and this is your theta, which is the power factor angle. So your P is nothing S times cosine this theta, which is the 0.8, divided by the power of the input, which you already have it, 32.32. 32.32, and this will give me 99% efficiency. And that's a very practical value for transformer, because transformers, they tend to have very high efficiency.